Power is work over time. We can also say that power is energy over time. Don't get this confused with pressure. Fortunately, we won't see both pressure and power on the next exam. So the P stands for power. The unit of power is 1 Newton meter per second. But remember that we called the Newton meter a joule, so it's 1 joule per second. And then further, we have a separate unit for power, which is a watt. And so 1 watt, if I want to convert that into its basic SI units, well, I would go back to this Newton meter per second right here. And I need, these are both in the MKS system. Convert my newtons, or not convert it, but break it down into its basic SI units. Remember, 1 newton is 1 kilogram meter per second squared. Right? Mass times acceleration. So 1 watt is going to be 1 kilogram meter per second squared. But then I have another, that's just newtons. I have another meters, and then I also have another seconds. So this is going to be seconds cubed. Okay? So that's how you find the basic SI units. Let me break that down again. So 1 Newton meter per second, that's equal to, a Newton is a kilogram meter per second squared. But then I have another meter, and I have another second. And so my basic SI units are the watts, like this, 1 kilogram meter squared per second cubed. Don't memorize that, but be able to work out the basic SI units for these more complex units as we see them. Putting them all in terms of the MKS system, the mass, the meter, the kilogram, and the second. Those are our basic units for all things in mechanics. You've seen the watt before, right? Like you have it on all of your appliances at home. And we will we'll study that when we get into electricity, that we'll look at how we determine the power rating of those electrical appliances and why it's important. But the power rating on those electrical appliances should at least give us some idea of how much work we can get out of, say, an electric motor. That if an electric motor consumes or puts out 100 watts, 100 joules per second, then we should be able to get at least some portion of that in physical work. However, that's dependent upon the efficiency, and that's another idea that we need to know how to use. The efficiency describes how much energy is converted in a particular task. It tells you how much usable energy you get.
When I read this in the book, it makes sense now. Because you know how you see, like, when you get new appliances, they have, like, this stuff that tells you how efficient it's.
Oh, yeah. Yeah, that's exactly what they mean. That if they say that they're 80% efficiency, that means that if it uses, or if the electric motor uses, say, 100 watts of energy, 100 joules per second of energy, then that means that you're going to get out 80 joules per second, 80 watts. That's your usable energy that you get out. So the efficiency is defined as the output power divided by the input power, and it's times 100 because it's a percentage. You can also give this in terms of work. It's exactly the same, though, because notice if I have output over input, if I just think about the units of power, this is work over time, this is work over time, so those per seconds will cancel out because they're going to both be just 1 second. How many joules per second on the top, how many joules per second on the bottom, and so they'll cancel out. So my efficiency I can also describe in terms of work, that the work that's output divided by the energy that's input times 100 as a percentage is going to be exactly the same. Both of those are equivalent. So for example, let's say that I have an appliance advertises 80%, or let's say 70% efficiency. How much usable energy do you get out if you put in 100 joules? All right, so our energy in is equal to 100 joules. I have an efficiency of 70%. So I can 70% equals my work out divided by En, which is 100. Times 100 because it's a percentage. See, I can just cancel these two, and I get my work out is 70 joules, the output work that I get. You'll have similarly easy numbers on your test that I'll give you numbers where you don't really need to use a calculator, that you can just work it out in your head. You don't use a calculator for test. All right? So, for example, what if it was 60% efficiency? How many usable? How much usable work would you get? 60. Right. So the calculation portion of this would be fairly simple. You've got nice round numbers like that. 100 joules. Just easy numbers to work with. Okie dokie? Y'all can do that, right? Huh? Hold on. Let's try this one. An engine has an efficiency of 20%. It produces an output work of 20 joules. How much energy was lost? So this is a similar question, but it's sort of reworded a little bit differently. I don't have a clicker. I'm sorry, my clicker is not working today, so y'all just try it on your own, and I'll ask you what your answer is in just a moment. If I have an efficiency of 20%, and I only get out 20 joules, how much energy did I lose? So you want to ask yourself the question, 20 is 20% of what? And that'll tell you the total amount of energy, and then ask yourself the question, well, how much energy did I lose? All right. What do y'all think? You can raise your hands. Do A, B, C, or D. You ready? 1, 2, 3, go. All right, I'm seeing a lot of B's. And that's right, that it's 80 joules. That I'm going to lose 80 joules because 20 joules is 20% of 100. Joules. And if I started out with 100 joules, but I only got 20 joules, that means that 80 joules were lost. I want you to have the right mindset. So that's part of this, is just understanding, you know, percentages, the language of percentages. But I also want you to understand the concept of efficiency, that engines are any device that when I put in a certain amount of energy, I only get back a portion of that. Where does the lost energy mostly go? Does it go into heat, sound, gravitational potential energy, or kinetic energy? Say for an engine. All right, what do y'all think? 1, 2, 3, 4. I'm seeing a lot of ones. And that's right. Have you ever cooked anything on your engine? Or you can, like you're. Have you? You've done what? I understand. All right. So,
It could also be sound.
it could be sound, but it takes a lot of energy to heat up your engine to that temperature. Yeah, Sarah.
So I have a question about this because I did get this right, but I'm just slightly confused. Because it's still energy, so why isn't it considered potential energy?
Oh, because thermal energy, when you have energy that's just heat, it's not very easy to harness. And so when your engine heats up, it's hard for you to save that energy and use it for something else. We consider that sort of lost energy.
Okay.
You do use it some in your engine. What do you use the temperature of your engine for? You know?
I actual heat.
Right, you want to heat your car, right? That's where it gets the heat for that. You don't have a heat element in your car. It just pulls heat from the engine. But mostly that heat is just lost. So then we don't consider it as potential energy.
Okay, so it's just okay.
Yeah, we consider it as a separate type of energy. I listed it in those different types of energy at the beginning. All right, so the answer here is heat. That most of that goes into heat, but some of it does go into sound. And depending on what your engine is doing, some of it might go into gravitational potential energy, and then some of it goes into kinetic energy too. That it drives, or that's not energy that's lost. I'm sorry. So it's mostly heat and sound. Okay, so temperature and heat. I want you to be familiar with the 3 different temperature scales. They are Fahrenheit, or Fahrenheit, it's German, to drive heat. Celsius, that's the most commonly used scale around the world, and then the Kelvin scale. And the Kelvin scale is the SI unit for temperature. For Fahrenheit, I want you to know what these scales are based on. Because anytime I create a scale like that, I have to have 2 different points that are defined and set. And that's what we've done with both the Fahrenheit and the Celsius, and also the Kelvin scale, is that we set different points, and then we use those different points to define what the scale is. And for both Fahrenheit and Celsius, they are based on the freezing and the boiling point of water. But for the Fahrenheit scale, we set the freezing point of water to be 32 Fahrenheit. And we set the boiling point to be 212. All right? And that means that between these 2 points, there are 180 tick marks. I don't know how that came about, but that's just the scale that we've set. The Celsius scale is a little simpler. It's just 0 and 100 degrees. So the Fahrenheit scale, the freezing point is 32 degrees. The boiling point is 212 degrees Fahrenheit. But for the Celsius scale, the freezing point is 0 degrees Celsius, and the boiling point is 100 degrees Celsius. So then, which is bigger, a Celsius, would that be A, or B, a Fahrenheit degree? If you have a change in temperature of 1 degree Celsius or 1 degree Fahrenheit, which of those is bigger? Is it 1 Celsius or 2 Fahrenheit? You can hold your finger up like this. Right. All right. Let's see. Which is bigger? So, what I want to know there when I'm asking that is which is the. Y'all can put your fingers on it. What I'm asking is which is a bigger change in temperature. And so between these 2 points, between the freezing and boiling points of water, there are 180 degrees on the Fahrenheit, but there are only 100 degrees on the Celsius scale. So if I change 1 degree on the Celsius scale, that's almost twice as much as a change in temperature on the Fahrenheit scale. Like a degree over here is like this big, but a degree over here is like that big. It's that much of a difference in change in temperature. So a change in temperature of Celsius is quite a bit bigger than a change in temperature for Fahrenheit. Almost twice 100 over 180, about 5/9 or 9/5 rather, almost twice. So the Celsius degree is almost twice the Fahrenheit degree.
How come we don't use it all the time?
Why don't we use the Celsius degree? Why don't we use the metric system? I think it just historical that we've used the Fahrenheit for so long.
But haven't other countries done that too in their schools?
Mm-hmm. Yeah,
We just
we're special.
figure stuff.
We are special.
I actually like in my car, I like to keep everything in metric.
Well, there you go. You can change back and forth.
Yeah, but I always keep the AC, I always keep the mileage and everything. I always actually have it in metric.
I think that's probably useful to think about things in a different way. All right.
So when people are like, oh, it's 32 degrees Celsius. Is that hot or cold? I don't know.
That's pretty darn hot, actually. Yeah. So, and my mother-in-law is from Finland, and so sometimes she'll slip back and forth because when she's talking with her Finnish friends and relatives, you know, they talk about the temperature in Fahrenheit. And man, if they had a 32-degree day, it'd be crazy.
Well, I don't know.
Yeah, but if they had, yeah, so anyway, you can convert between Fahrenheit and Celsius. I'm not going to make you do this, but I just want you to be aware that you can do this, that there are these formulae to allow you to convert. The Fahrenheit is 9/5 times the Celsius temperature plus 32, and the Celsius temperature is equal to 5/9. Remember, this 9/5 comes about as 180 over 100. That's where the 9/5 comes about. And this 32 comes about because there's an offset from 0 to 32 for the freezing points. So they're not enigmatic equations. Those numbers are there for a reason. To change from Celsius, it's 5/9 times TF minus 32. Again, not going to make you convert Fahrenheit to Celsius. I do want you to understand how they differ, the Fahrenheit and Celsius, and what they're based on. But you can convert them. So just for example, if I wanted to convert 37 degrees Celsius, 37 degrees Celsius is 9/5. 37 plus 32. Just for reference, that's, like I said, that's a hot day. That's 98 degrees Fahrenheit. And for Celsius, if I wanted to convert 70 degrees Fahrenheit, I would say 5/9 times 70 minus 32. That's equal to 21 degrees Celsius. So that's a nice, comfortable day. This is 70 degrees Fahrenheit. And this is equal to 32 degrees Celsius. Some temperatures that you should know. Room temperature. Is about 20 degrees Celsius. And body temperature is about 37 degrees Celsius. So just know those good reference points. It gives you a feel for, is it a nice day outside if somebody says it's 20 degrees Celsius, or is it really hot outside, which would be about your body temperature.
We need those temperature and body temperature.
Huh?
We need those.
Yeah, I want you to know those sort of basic reference points for temperature. Okay, so do know these things. You'll see them on some of the old tests. I might just ask you, it's a nice day outside, what's the temperature? And give you a series of temperatures. And if I put 70 degrees Celsius, obviously that's not a very nice day, right? All right, the Kelvin scale is a little bit different. The Kelvin scale is based on absolute zero. We talked about absolute zero back when we talked about, what was it? We were talking about, what was that?
Freezing things.
Yeah, freezing things. Oh, the viscosity. Remember we were talking about viscosity? and how when you got this helium superfluid, it would get zero viscosity. It could actually go through a barrier. So absolute zero is the absolute lowest temperature that you can get. It's going to be 0 Kelvin. And that's when all motion of molecules ceases, that you don't have anything moving around. And that's a theoretical limit. You can't actually reach it because you can't stop an element or an atom from vibrating. But you can get darn close. In fact, we have an instrument just down the hall, our nuclear magnetic resonance. It's cooled with liquid helium, and it gets down to really close, millikelvin, just above absolute zero. So as you're walking out, you can look out. It's just sort of right to the left. You might see it's a big metal cylinder container. You saw it?
I think it. What I think I saw.
Yeah.
A big canister.
Big canister. Well, one of the canisters is the liquid nitrogen, but the one that's off in the corner is our NMR, nuclear magnetic resonance. Maybe when we get to magnetic fields, maybe we'll go look at it. It's kind of cool. So it's based on absolute zero, and it's based on the triple point of water. The triple point of water is when water exists as, goodness bless you, a liquid, solid, and vapor, or gas, all at the same time. There's a particular temperature and pressure for water. It's really close to 0 degrees Celsius, which is the freezing point of water. Just a little bit above, I think it's like 0.1 degrees Celsius. But then also a particular pressure, and water exists in all three states at exactly the same time. Did you know that? You could have that? That you can have water exist as a solid, as ice, as a liquid, this is liquid water, and as a vapor all at the same time. So it's about 0.1 degrees Celsius. So the Kelvin scale, yeah.
Is that what happens in those caves?
No. No, the triple point of water occurs at a very controlled set of conditions. I don't have a video. I don't think that it's very exciting. I think I've looked for them before. But, okay. Like I said, it is very controlled laboratory settings. I don't think it occurs in nature that often. The Kelvin degree is the same. Okay, so Kelvin scale based on absolute zero and the triple point of water. If I look at say a thermometer, if I have absolute zero down here, and up here I have the triple point of water, I say that this is 0 Kelvin, and this is 273 Kelvin. Right? The 273 comes about because they want it to link up with our Celsius. Turns out that absolute zero in the Celsius scale is minus 273. You don't really need to know that right away, but you do need to know that the Kelvin degree is the same size as a Celsius degree. I don't mean that the temperatures are the same. They're like 70 Kelvin is the same as 70 degrees Celsius. That's not what I mean. What I mean is that a change in 1 Kelvin is the same as a change in 1 degree Celsius. And that's why we have this funky 273 up here, because that seems kind of strange, right, to have the 273. It's to link it up with the Celsius scale, so that this is true.
So 0 Kelvin is negative 273.
That's right. 0 Kelvin is negative 273. I'll write that if that helps you. 0 Kelvin is negative 273 degrees Celsius. It's actually like 273.1 because it's based on that triple point. And 1, how do I want to do this? A change in Kelvin is equal to a change in degrees Celsius. Also, just as you might have heard the language and you might have picked it up in your book, that we don't call a Kelvin a degree, that we call a Kelvin just a Kelvin. So you don't say 1 degree Kelvin, you just say 1 Kelvin. And that's based on He was a physicist. Lord Kelvin. I don't know what his first name was. Lord, I guess. Right? We already talked about heat, but heat is the transfer of thermal energy. And the total amount of energy inside an object depends on the type and amount of material. This is called thermal energy. All right. Thermal contact is when two objects are able to transfer heat. So you can be in thermal contact with an object without actually touching the object. Right? If I have something that's really hot and I just stand up next to it without touching it, I have some amount of thermal contact with that object because the object is transferring heat from the thing to me. Right? Or if I touch the object, I have direct thermal contact with it. If I hover over it, I have thermal contact. It's not as good a contact, but I still have thermal contact. Or like with the example, we like to camp, we like to roast marshmallows. And which is better, to use a wooden stick or a metal stick? Well, it's better to use wood. We use metal because the wood will just burn up in the fire. But it's better to use wood because the wood limits the thermal contact between you and the fire. Because if you hold...
Oh, I thought when it said camper, I was thinking like an actual camper you would sleep in. I was like, what are you talking about?
Oh, no. The camper, like the person camping. So if you stick a metal rod in a fire, eventually it's going to burn you because the heat will transfer from the fire to your hand. Now they make marshmallow sticks they have a lot of air in them. They sort of limit the contact with these little plastic pieces, but you still make thermal contact with the camper. So
is there a way that the wood can go on the fire without it burning?
Not really. I mean, if you use a green piece of wood that has a lot of sap in it, that'll keep it from burning right away. But eventually it'll burn up, of course. All right. Y'all like to camp? We like to camp. Me too. We're hoping for some cold weather soon so we can go.
But what about lightning? Or is that completely different?
Now, lightning is a transfer of electrical energy. We'll talk about it later. That you have two sets of charges between the Earth and the clouds, and there's a discharge between those sets of charges. Right, because of the electrical field.
So it's true that lightning starts at the ground and then reaches the clouds?
All right, we'll talk about that later. Thermal equilibrium occurs when there is no flow of heat between two objects. This only occurs when you have the same temperature. If I have one object that is hot and one object that is cold, I don't know why we draw cold objects blue, because you know blue is actually hotter than red. Y'all know that? Like the blue flames are hotter than the red flames. We'll talk about that when we get to light. But anyway, that's how we do it. The hot, you will always have a flow of energy going from hot to cold when you have a flow of heat. But if I have two objects that are exactly the same temperature, T and T, there's no flow of heat. Because they're the same temperature. We would say that those things are in thermal equilibrium. I think I have that written here. Let's see. No, but let's say that. So these things are in thermal equilibrium.
So when you used to get yelled at for leaving the door open, and your mom would be like,
I didn't get yelled at for leaving the door
"You're
open.
letting the cold air out." It's actually you let the hot air in.
Right, you're letting the hot air in. Surprise. No, not going to get. All right. Okay. Those are some of the basic laws of thermal physics. These are some of the basic laws of thermal physics. That the definition of thermal equilibrium, the definition of thermal contact. So be familiar with those. These ideas of thermal contact and thermal equilibrium. All right, there are three phases of matter. I think y'all know this. Right, I mean, you've had it since probably first grade almost. Solids, liquids, and gases. What's that?
I can't remember what, but I know I never forgot it.
Yeah. Remember, liquids and gases are both fluids. That's important for the previous chapter that we had. When you have a phase change, you go from a solid to a liquid to a gas, and each of these require energy to be input into the system. Or if I'm going backwards, from gas to liquid to solid, I have to take away energy, right? If I want to go from a gas to a liquid, I have to cool it down. If I want to go from a liquid to a solid, I have to cool it down even further. And so I can have these changes between phase by putting in energy into the system. And that energy is thermal energy. It makes the particles begin to move more with respect to one another. And then that causes it to go from the solid to the liquid to the gas. The gas, the particles are going to be moving the most. The liquid, less than that. And then the solid, the particles are pretty much locked into place. They're vibrating, but they're not moving around like they are in the liquid and gas.
So what about this plasma that's in the picture?
I have a picture. I have a plasma in it. Okay, yeah, so a plasma is a different type of matter. It's sort of a special case. In a plasma, that's why it says this recombination and ionization. What that means is that the electrons and protons are split apart. So if you've ever been to like one of those prank stores, like what's it called in the mall? Spencer's, yes, where they have like the turds in a box. You know, have y'all been to Spencer's? You can admit it. Yes. They have those little balls outside, and if you put your finger on it, zzz, it comes up. I've seen those. That's a plasma. And it doesn't necessarily have to be hot, because those little balls, they aren't hot. But what it does is it ionizes the gas. It splits apart the protons and electrons. Where else do we have plasma? No, that's a different type of plasma.
In the surface of the earth?
Not on the surface of the earth, but the surface of the sun.
Oh, we get the little things.
Right. Is it raining?
Again? It's not yet. But
Okay. Okay. Anyway, the sun is a big ball of plasma. That means that all the electrons and protons have been ripped apart. They've been ionized. And it's a plasma because it's really hot. That the heat of the sun has caused those atoms to lose their electrons.
That's what you can't go near it.
Yeah.
That's what causes the little sun things.
The sunspots?
So the little, or is that the electrical thing?
No,
It
the
shoots out of the sun?
the flares?
Yeah.
No, that's different. We'll talk about that though when we get to magnetic fields. Just a second, Sarah. That when you have flares on the surface of the sun, you get these magnetic fields. They're like big looping magnetic fields, and the plasma, which is just a charged substance, will follow along those magnetic fields. It's kind of cool, actually. I'll show you a video later. Sarah?
I'm just wondering, so because it can jump from solid to gas, does that just require more energy, or is there something else involved in that?
No. We can go from a solid to a gas with more energy.
Okay, so it's just more energy.
Yeah, let me show you this diagram. I'll explain it a little more. But first, specific heat describes how much energy is required to change the temperature of an object. That's required, but with no vowels. You'll know it. I told you my trick, right? Of not writing the vowels. I'm taking Hebrew. I think I told y'all. And in Hebrew, they don't have any vowels. Or in like ancient Hebrew, there were no vowels. All they had were consonants. And then later, like the Masoretes, they came along and they said, well, we got to get some vowels in here. Nobody knows what this is. And so then they made like little points, little symbols that were attached to the consonants.
You taking that here?
No,
Oh.
no. It's a crazy class. Oh, you think this class is hard? Oh. No, I know y'all don't think this class is hard. But describes how much energy is required to change the temperature of an object. You might remember this from your chemistry in high school. It was the QMC delta T. This is the specific heat. That's this constant. Some materials just require more energy to raise their temperature. Like, for example, if you go to the beach, whether at Grand Isle or over into Mississippi or Alabama or wherever, the sand and the water have different specific heats. Which of those have a higher specific heat? Which requires more energy to raise its temperature? The water. That's why the water is always cooler than the sand, at least during the daylight hours.
So then what about when you go to like the different parts of the ocean and some waters are warmer?
That's because it's different depths, or because you also have currents. But if you have shallow water, there's not much water there, and it heats up more readily because M is smaller. This describes how much heat is required to change the temperature. If C is big, that's the specific heat. It means you need lots of energy. If M is big, you need lots of energy too. And so in shallower waters, M is small. There's not much mass there, so it heats up more readily. But as you move out to deeper waters, M is bigger, so it requires more energy.
What if you go to California? Is the water over there supposed to be warm? No?
Yeah, I think they get more sunlight in California. No, I don't know. I'm not sure that it's warmer. I mean, it depends where you are. Huh?
Oh, I don't know. Let's get it together. I've always thought that different, like go to the Atlantic or whatever, that some of it is warmer than like you go to the Gulf.
I think it's, there are bigger things like currents and what latitude you're at and various other issues. All right, so specific heat describes how much energy is required to change the temperature. And then latent heat, somebody asked, Sarah, I think you asked, has to do with how much energy is required to change the phase. Latent energy? Oh, you've heard it. I know you have, you just forgot. Now, you should have seen this diagram somewhere along the way. I know I was in the 8th grade science class at a school this week, and they showed this diagram. They had a test on this diagram, in fact. This shows the energy that you input to a substance and the resulting temperature change. And so what happens here, I start with ice. And I put energy into the substance, and it just causes it to change temperature. And so here, I have ice right here. Here, I've raised the temperature of the ice up to 0 degrees Celsius. That's the melting point. But it's still ice, but just the warmest ice that you can have. And then I have to put in more energy, and this is converting the ice to water. So along this line, I have both ice and water because I'm beginning to put in the latent heat of the ice. Changing it to water until I get to, I'm still at 0 degrees Celsius, but now I don't have 0 degrees Celsius ice anymore. I have 0 degrees Celsius water. It's all water. And then I put in energy, and I raise the temperature up to 100-degree water, 100 degrees Celsius water, no steam, just really hot water. And then I raise the temperature, or I put in a lot more energy, because actually the latent heat between the liquid and vapor stage, our vapor phase, is a lot. Notice it's a lot of energy here along the x-axis to go from water to steam. That's why if you have 100-degree water and 100-degree steam, which is going to affect you more? Which is going to harm you more? The steam. Because the 100-degree steam has a lot more energy than the 100-degree water. And it's not so much the temperature, it's the energy that's involved. We'll talk about this when we get in the next section of this chapter, that the latent heat of our material is very important for evaporative cooling, which our body relies upon a lot. Right? When we sweat, that cools us off, because when the water on our skin evaporates, when it turns into a vapor, it takes away this amount of energy from our bodies. And it's very effective at cooling. At least not so much here, because sweat doesn't evaporate that easily because it's so humid. But in drier areas, that's why dry areas seem really nice, because your sweat just evaporates. Your body cools so effectively.
Actually, one of the places I go where my family lives in Mexico, Jalapa, it's like super humid, but it's at such a high altitude that the water actually, the vapor actually cools you off. Like it's nice and cool year round.
But it's really humid at such a high altitude.
Yeah.
I've never heard of that. That's interesting.
That's like scientists don't.
Huh? We need to get a scientist down there?
Maybe you need to take a
I'm sure
vacation.
I'm sure they have science. Yeah, I'm sure it's really nice.
So,
Is it
like,
nice?
when we,
Super beautiful. It's
Yeah, I
like
bet.
climate, the whole thing.
Yeah.
Just make sure you bring extra brake pads.
His parents are from Mexico. Or your dad's from Ecuador, right?
No, my mom's from Mexico.
Your mom's from Mexico. Your dad's from New Orleans. But his parents were from Ecuador or something?
My parents just come because my dad, he was born here in the in the New Orleans area, but like his father's from Honduras,
Oh, okay.
and his mother's from Germany.
All right.
And
Anyway, not on the test. Not on the test. All right.
but isn't it harder to breathe, kind of like when you're at a higher altitude?
That's just because there's less oxygen.
Oh, okay. Because we went to the Grand Canyon, and obviously I'm used to being down here, and it was so dry. I was like, oh.
But you could, yeah, it was harder to breathe because there's less oxygen. Okay?
Okay. Can you calculate latent heat?
Yeah, you can calculate the latent heat.
Because what you said makes me wonder.
I'm going to show you how in just a moment. When we talk about calorimetry is the next question. All right? So let me just remind you that 100-degree steam has more energy than 100-degree water.
Eighth graders are smart nowadays.
Yeah, they were doing this. It was on their test, and it was a tough test. Has more energy than 100-degree water.
It's like I used to watch Are You Smarter Than a Fifth Grader, and I'm
All right, so calorimetry is the study of how energy and temperature and phase change. The study of energy and how temperature and phase change. All right, I have two formulae. It'll help you to, I think they're on the equation sheet. You're not going to have to calculate anything, but it's important. We've already addressed it a little bit. Q is equal to MC delta T, and then also Q is equal to M times L. And this can either be latent heat of fusion or latent heat of vaporization. That's our latent heats. So just to identify these things, this is our specific heat. This is the energy, the thermal energy. This is mass. Mass is same on the other one. And then this is our change in temperature. All right, so for example, if I want to know how much energy is required to change a certain amount of ice to water, I take the mass of the ice and I multiply it times the latent heat of fusion. And that'll tell me how much how much energy is required to go from ice to water. Let me further explain this. LF is the latent heat. I see you over there, Kate, just a second.
Yeah, no, that's what I was asking.
The latent heat of fusion, that's like a solid to a liquid. I think fusion, when you fuse things together, it makes a solid. And the latent heat of vaporization is LV. And that's how we get from a liquid to a gas.
So you said fusion was solid to a liquid?
Yeah, this is solid to a liquid or a liquid to a solid. So it can tell you how much energy you have to put in to go from a solid to a liquid, or how much energy you have to take away to go from a liquid to a solid. Both of those require either some change in energy.
So anytime you're going backwards from solids, liquids to gases, liquids to solid, it's going to be taken out.
If you're going from gases to liquids, gases have more energy than liquids, so I have to take away energy.
Okay.
If I'm going from a liquid to a solid, I also have to take away energy.
What if it's going from a solid straight to a gas?
You still have to put in a bunch of energy to go from a solid to a gas.
Well, which one would that be? Would that be fusion or?
Oh, I don't know. That's sort of a special case.
So
All right.
vaporization is liquid to gas and gas to liquid.
Right. Mm-hmm.
So what part of this do we need to know for the test?
Okay, I want you to.
It's modified.
I understand. So you need to understand this diagram and what it means. All right. With that, if I put in energy, I change the temperature, and then if I put in energy here, I change the phase. And in response to that, we're not going to have to use these formulae, but I might ask you something like the water question. Like, what if you have a bigger mass of water? How does that affect the change in temperature? If I have a bigger mass of water, it requires more energy to increase the temperature of that water, right? Because I have this dependence on M. And so if M is big, then Q is going to be big for a certain change in temperature. I also want you to know specific heats of different materials. That some materials, like sand and water, have different specific heats. And material with a big specific heat is going to require more energy to change its temperature. Water has a big specific heat, and therefore it's very difficult to change its temperature. But sand, on the other hand, has a very low specific heat, so it's really easy for it to heat up. That's why it gets so darn hot, by noontime, and the water stays cool. So understand the specific heat and what effect that has on the change in temperature. And then also, we're going to see this all again when we do evaporative cooling. But I want you, the latent heat of fusion, latent heat of vaporization. And that's the amount of energy to change phases. Does that answer your question, Annette?
A little bit.
A little bit. That's a good question.
Yeah, there's a lot.
Yeah, read the book too. The book will help you on this. Okay?
So the latent vaporization. So the latent fusion goes from solid to liquid and liquid to solid. What is the latent vaporization?
Latent heat of vaporization goes from liquid to gas or gas to liquid. Vapor, right? That's a gas.
Yeah.
Okay. We're almost done. Just have a couple more things. Let's try these questions, y'all. The Fahrenheit scale is based on the freezing point of water, and then which of the others? Is it the deprivation of free radicals, the boiling point of water, the freezing point of ice, or absolute zero? What do y'all think? 1 through 4? All right, it's 2, right? It's based on the freezing point of water and the boiling point of water. Which of these changes in temperature is smaller? If I have a change in temperature of a Fahrenheit, a Celsius, degree Celsius, 1 Kelvin, Or do they all represent the same change in temperature? Which is smallest? 1 through 4. I'm seeing some ones. A Fahrenheit, and that's right. So a degree Fahrenheit, because the Fahrenheit scale is between 32 and like 212, that means that I got a bunch of little bitty tick marks between those because there are 180 tick marks. Whereas for the Celsius scale, it's 0 and 100. I just have 100 tick marks on that. So that's a smaller, the Fahrenheit is a smaller change in temperature. Latent heat of fusion. What is latent heat of fusion? Solid to liquid, solid to vapor, liquid to gas, or gas to liquid. What's the latent heat of fusion? I'm seeing some ones and some no answers, right? So the latent heat of fusion is solid to liquid. And always remember that because fusion, you like fusing things together to get a solid. All right, so that tells us the solid-liquid transfer is the latent heat of fusion. And then which contains more energy? Don't worry about the enthalpy. I think your book might have used enthalpy, but just which contains more energy? Water at 100 degrees Celsius or steam at 100 degrees Celsius are both the same. Right, the steam. So the steam has a lot more because it absorbed that latent heat of vaporization to all become steam. It's much more energy, and that's why steam is so much more damaging. All right, just one last thing here. There are 3 methods of heat flow. They include conduction, convection, and radiation. Oh, you know them. They were in middle school. It's a middle school topic. Or it is now. Maybe y'all didn't cover it in middle school.
I just don't remember the radiation one. I remember conduction.
Good.
I only remember those because your oven.
Huh?
Because of an oven, like you can get a convection.
You can. What is a convection oven? What's the difference between a regular oven, that would be a radiation oven. They don't call them radiation ovens, do they? But they should, because that's what they are. What's the difference between a radiation oven and a convection oven?
Doesn't the heat come from the water?
In what? The radiation or the convection?
Yeah, the normal oven has like a coil
Yeah,
that heats up.
the radiation oven
But
has
the
a coil.
convection is all around.
Well,
Is it convection then?
the only difference, they have a fan. They have a fan that blows air and it moves the heat around more evenly.
Because convection is heat transfer through fluid.
Right. Heat transfer through the motion of a fluid. So in your radiation oven, call it a radiation oven from now on. I think that would be kind of cool.
I use that in my car all the time.
The radiation oven or the convection oven?
More like opposite effect, but convection. Because like I'll point all my AC vents upward so that it gets all the warmer air towards the top.
Oh, look at you. Yeah.
It can actually feel the air sink towards the back.
Yeah, we got one of those air fryers. Yeah, cool.
Good. All right, look. I want you to know this formula. You don't have to, we're not going to calculate it with anything with it, but it is kind of important. We'll spend the rest of our time on this. This is the rate of conduction. It's equal to K times A times delta T divided by D. This describes how much energy per time is conducted by a material. So this is energy per time. And I think that the relationships are kind of intuitive. So let me just define what these are. K is your thermal conductivity. It describes how readily does a material conduct thermal energy. Wood or metal, which has a bigger thermal conductivity? Metal, right, metal. If I stick a piece of metal in heat, it heats up really quickly and it conducts the energy more readily. A is the area. You said that with great conviction. I appreciate that. I really do. T is the difference in temperature. And D is the distance between two objects. So imagine I have two objects. We'll say that this is an object at T1, and then this is an object at T2. And they're connected by some material. A bar, say. All right? Q over T, let's say that T1 is bigger than T2. So it's like T1 is the hot object. That means that I'm going to have a rate of energy transfer, Q over T, going from T1 to T2. That the heat is going to move from here to here. And the rate at which the heat moves through this bar is going to be dependent on all of these things. So if this bar is more thermally conductive, has a higher value for K, that means it's going to move energy more quickly. So if K is big, say metal, for example, then Q over T is big. Likewise, if the area of that bar, so if it's just like a thin piece of metal, like a thin piece of copper wire, not much energy transfer. There's just not enough material there to transfer the energy. But if I have a big old honking piece of copper wire, or a big copper pipe in between the two, then I'll get more energy transfer. You can think of it as a pipe. If I have a bigger pipe, I can move more stuff. So if the area is bigger, this cross-sectional area Q over T is bigger. And then similarly, if my temperature differences are bigger, and we said if there's no temperature difference, there's no transfer of energy. And if I just have a really tiny temperature difference, it's going to take a while to transfer that little bit of extra energy.
Did we talk about this in chapter 2?
We did, I think. Yeah, I'm pretty sure we did. It was very similar, except we were talking about fluids there. But a lot of it's still the same. You can think of it in the same way as fluids. If the area is bigger, Q over T is bigger. If the difference in temperature is bigger, Q over T is bigger. If the distance, if D is bigger, that means Q over T is smaller. Right? It's an inverse relationship. If you pull those objects really far apart, it's just harder to transfer energy. All right? So know those relationships. You'll probably see some questions about those.
So in other words, just like usual, everything at the top is going to go higher.
That's right, just like usual. Yeah. And just two quick definitions here. Convection requires the flow of a fluid. And radiation is the transfer of energy by light waves. We'll have a whole chapter on light waves. And we'll talk more about these after our test, but radiation oven, our rad oven, it just has a heating element at the bottom, and it puts out infrared radiation, and it cooks your food. A convection oven has that same heating element, but then it also has a fan that takes the heat and moves it around inside the oven. So your radiation oven, no fan, just radiation. just light waves coming out of this element, infrared waves. Convection oven has the element, and then it has a fan that blows that stuff around. Makes your food cook faster and more evenly.
So how come, like, sometimes when you're reading a recipe and you talk about, like, cooking certain things, it says if you're at, like, a higher altitude?
At a higher altitude, your atmospheric pressure is less, and so things cook a little differently. All right, people? Remember, read the book, read the notes, study the old tests. That's how you'll do well on this test, okay? Read the book, read the notes, study the old tests. We have about 4 days, so spread it out. Don't do it all the last time, okay? If you haven't started, you need to start today. Please, please, please start today. Well, have a good day, okay?